And because of that, we have been able to kind of achieve order of magnitude better performance than what is currently kind of the. So we are moving in the new era, and this kind of shows how our society has moved from agrarian revolution, where wood was used to kind of produce energy, then coal, industrial revolution, transportation revolution, then we went through the internet revolutions where we were using bytes to kind of measure the value of a specific system. And now we're kind of entering the AI revolution, especially generative AI, where tokens are going to be what's kind of driving a lot of the compute. And what groq has built effectively is a mega token factory. And I'll kind of explain why we kind of connected to a factory, an assembly line, and so on as we move forward here. So I'm not going to go over these results. These are some of the kind of posts that have the internet. Seeing significant improvement in the latency. In other words, you can see almost an order of magnitude improvement in how many tokens per second we can produce. And then you can also see the actual latency and the throughput where groq sits in a quadrant here on its own, where you see everything that's kind of GPU based is sitting in a different quadrant. So yeah, so what I want to do is kind of explain how we have gotten here over the next couple of slides. And feel free to stop me at any point to ask questions, and we can dive into it. I'm not going to go over the demos. A lot of them are already online. You can grab and take a look at them. You can play with groq chat on the groq website as well. So I'll just jump into the technical kind of details, and I'll start with really the full packaging hierarchy that groq has enabled. So from the left, you see a groq chip. This is a custom purpose-built accelerator. And it was built in a very unique way. When groq started, we didn't start like many of the AI startups where we would build the silicon right away and then figure out how we program it. We started with a software first approach. In fact, the first 6 months of groq, we never touched RTL up until we figured out that the software they were building would be easily mappable into the hardware. And what we produce is this very regular structured chip that's integrated on a PCIe card. 8 of those cards make up a groq node. And then 9 of those groq nodes make up a groq rack. So we have 8 groq nodes plus a redundant groq node inside the rack that we can actually swap in the case of a failure. So we have some redundancy in the system. And this system is really exceptional at processing anything that is sequential in nature. And the large language models happen to be exactly that, where the next token is always a function of all the previous tokens ahead of it. So it's really sequential in nature, and that's where we really shine. And it's not just large language models that we shine at. We cover a number of different applications. It's just that is kind of a key highlight for groq at this particular point in time. All right, so what I want to do for the next bit here is start with the groq chip, and then I'll move into the groq system. So we'll start with the silicon here, the sand, and we'll move all the way to the cloud.
Maybe just a quick question before we go there.
Yeah.
Given that you started in 2016, if I'm not wrong, did you have to pivot since then, or were you just visionary and you knew that this specialization is going to pay off along the way? Like, yeah, what's the story there?
Yeah, so there's definitely some luck in the process, but we started really pushing for hardware that's easy to program. So if you look at the current biggest challenges for AI hardware is not how many tops you get that your chip can is capable of, is can you map these really well-behaved data flow algorithms into a non-deterministic hardware. And I'm going to touch on that a little bit. So that was the initial push, Alexa. The push was also for sequential processing. But LLMs we really stumbled on, and they just kind of highlighted the value that really groq can bring to these type of workloads.
Got it. So it just turned out that transformers run really nicely on groq hardware, as opposed to you waiting for 2017 and seeing that it's kind of started to become popular and then focusing on supporting it better.
Yeah, I wish we had a huge foresight, but we definitely saw the need for hardware that is really accessible to everybody. We don't do large language models ourselves. We don't train them. We just run them fast. But what we wanted to build is this really fast accelerator with easy to map software. And as I'll show in the next group of slides, that we have over 800 of the best known AI and HPC type of workloads that are already compiling into our hardware. So that's really a huge amount of models, and they're all kind of multiple X better than GPUs. So we're not only can compile the software, but we can really run it efficiently.
Awesome. Maybe just one more question on my side is, what was the value proposition? Because you started the TPU team back at Google, you and Jonathan, if I'm not wrong here. And so what was the value proposition initially? You just thought that the rest of the world has to have something similar to a TPU, or you had some insights of how to
for the rest of the world, not just big companies. But the other thing that Jonathan noticed is that these devices are notoriously hard to program. So he really started from scratch, and he really spent a lot of time figuring out this software first approach. And this is what resulted in our kind of renaissance in the number of machine learning and HPC models that we've been able to support. And this kind of came last year. So we kind of hit that tipping point last year where we can support all these models, and we had efficient hardware to run it on. And then LLMs became open source with Meta kind of releasing Llama, and that really kind of was the second derivative of our kind of movement forward.
Awesome. Thanks a lot.
Yeah. Yeah, so I'm gonna dive into the details of the chip. Feel free to stop me if you have any questions. I think we're all kind of aware of Moore's Law. Moore's Law was this law that basically said that we would be able to double the number of devices per unit area every 1.5 years, or at least the economy of it would make sense. But as we've kind of moved forward, we're seeing this significant slowdown, and we're now at the point where Moore's Law is kind of giving us maybe 3% per year increase in number of devices per unit area. At the same time, the compute demands are exploding. So we've tried multi-core approaches, which is also the path that many AI companies have taken for kind of AI acceleration, including the GPUs. There's many cores on it. But these are notoriously hard to program, and we've kind of still seen the plateau in performance as we move forward. So one way to address this was to kind of enter this golden age of computer architecture, as David Patterson has called it in his famous Turing Award talk. And this is really custom hardware for specific applications. So we have GPUs that have kind of started for gaming applications. This is like a 25-year-old technology that's only recently been repurposed for the applications of AI acceleration. But then you got specific AI accelerators like TPUs, video processing units like VPUs, data processing units. So we've seen a lot of like an alphabet of mix of these processing units. And groq's language processor unit is just one of those domain-specific architectures. But the way we have pursued the LPU is very different from most of these approaches, and I want to kind of describe that in the next couple of slides. Was there a hands up? Did anyone want to have a question?
Igor, you can just continue, and I'll be curating the hands. That's easier.
Okay, sounds good. All right, so we wanted to build a chip, and as I mentioned, we wanted a chip that we can easily map software algorithms into that hardware, right? So we didn't touch RTL until we were comfortable with the approach that we have taken. Now, if you look at the landscape, these AI algorithms are data flow dominated. They're really well behaved. You can statically kind of schedule them. They're highly parallel vector operations, so they use vectors or matrices. So they're really well behaved algorithms. On the other hand, we have really powerful hardware. So you keep hearing about the number of